Yeah, I'd be very happy to, Orlando. So last question, homework five. We'll make that our first question to start us out today. And now that you mention it, I might as well pull that one up. So this one right here,
Yeah, that's the one.
gotcha. We'll throw it into the notes right here ahead of example 7. Well, it looks like class has officially started. Welcome back, everyone. Just getting the document lined up. So we're nearly done with this section 6.2. Congratulations, folks. I know that graphing all these trigonometric functions is sometimes the slog when it comes to the trigonometry course. Once we get through section 6.1, 6.2, we're returning to more normal kind of work that you saw in chapter 5. Then chapter 7, or excuse me, yes, chapter 7 will be more of the same kind of stuff. So we won't be plotting forever. We're about to change gears. We're on example 7 now, but we'll start with a question from the class to start us out. And also for the other announcements, down below we have midterm weeks coming up, but this is not an exam week. There's no exam, there's no project, there's no quiz or anything like that. All we're going to do on midterm week is just report your current course score at the end of this week on Friday. So it'll be whatever your score is up here, I'll make a new entry called midterm grade, and it's just going to duplicate that score. What any questions, folks, about the upcoming midterms or anything along those lines? Oh, I lost participants window. There we go. Okay, well, let's start off with the question that was asked to begin the class. This one is from assignment number 5. We need to determine amplitude period phase shift midline equation and sketch the graph over one full period. To get us started on this one, exactly. No matter what you see here, just peel off that negative and you're all set. So amplitude on this one, absolute value -3, just comes out as a 3 to start us off. Then for period, we are dealing with a cosine function, so 2 pi goes here. And what would be in the denominator? Anyone spot what it should be?
It'd be a pi over 4.
Absolutely. In class and in Zoom, pi over 4 will go down to the denominator here. Once I draw pi correctly, there we go. It looks a little bit more like a pi. There's a good time saving step on this one. What you're really going to do is take 2 pi, multiply by the reciprocal, 4 over pi. So once you start to plot lots and lots of these things, that's probably what your go-to method is going to be each and every time. Pi cancels out. So that and that are gone. And we get a period of 8 for this function. So we'll be graphing over a length of 8 on this. Next thing we need is phase shift. And for phase shift, we're looking at this part of the function. We negate the sign, so it's going to turn into negative pi over 2. And beyond that, we still have to divide by something. Anyone recall what goes down below here again?
It'd be pi over 4 again.
Yep, once again, just throw that down there. And if you look at the color coding on every one of these functions we've done, that's a nice and foregone conclusion each and every time. So it becomes a pattern that we just follow our muscle memory on pretty much. So now negative pi over 2 times 4 over pi. Let's make this look like an actual cancellation pen. We'll cancel this way. 2 to go to 4 2 times, so -2 for phase shift. So this one is a little bit scarier than the other ones because it also has this going on for it. This is not a question to ask a lot. It's more just for homework questions. They're kind of fun. And that one is the midline equation that we have to deal with. Because it's a horizontal line, it starts off like this. Let me first put down what we're working on, the midline equation. There'll be a y equals, and well, it's not so bad, right? Whatever is here is your midline equation. Y equals 4. Well, this is the preliminary analysis. Usually we do a little bit more over here to get started, but any questions, folks, to that stage?
So I forgot to put the negative for the phase shift. So I already turned my homework already. Totally forgot about that.
If you like, you can, after class today, just make that change and send in another email with maybe just that problem or something like that. And I'll accept that as a correction on your homework since I'm really only going to be grading them probably on Friday. But other questions so far? Okay, well, let's now put down the rest of the analysis we didn't need to get through this kind of problem. We need to know where the thing starts. Anyone recall what should go right here for the cycle start? Absolutely. So whatever you said phase shift is, that'll go right there. Good idea to write this in. As a formula, it helps with memorization. So we have our start there. It'll end at phase shift plus period. So now we're looking at two more values, -2 for phase shift plus 8 for period, giving us a value of 6. And finally, increment. That's long to write out. So a good shorthand I saw earlier today is I, if you'd like to use that. I for increment makes sense. For the increment, we'll take 1/4 of this. So the formula is 1/4 period. So 1/4 times 8, giving us a value of 2 to start. So there's the follow-up analysis. Now we need to start writing down things. But when we start to graph this, we need to be really careful. And the reason is, although the x-axis is important, that's not where the curve is oscillating around. This transformation of cosine is going to be oscillating around y = 4. So we want to go up 4 to start. There's our midline equation. And now that if you've gone up 4, there's a little bit further trickiness. Anyone see how much we should go up and down around 4? Exactly. If the amplitude is 3, we go up by 3 more for a height of 7. So 5, 6, 7. Then again, if the amplitude is 3, go down by 3 from 4. 3, 2, 1. And how should we color code that? That's an interesting concept. Amplitude combines with the midline equation to give those two values. I'll just circle it in or purple, I guess, as the color there to show how that goes. Other things I forgot is the start is at -2, so I probably should have put some extra space here. Here's -2. Their increment is 2, so here's our first check mark. The second one is there. There's the third, the next, and the next. To get all of these, we just add 2 each time to get to the next one. And we ended at 6 right there. So that's pretty much the work we would have to do on this. I'll leave doing the sketch for cosine up to you folks. But the trickery for cosine is there's also a negative, so you have to reflect your graph across this line as well, that midline equation. But any other questions, folks, on running through this kind of problem?
Yeah, I think I thought the midline equation was supposed to be y is equal to 4, but I just drew it as it is, like not at 4. I just do it with an amplitude of 3 and 3, like 3 and -3.
So you're saying you drew kind of like your x-axis at
Yeah,
this
that
height
is true. That is true. Yeah.
Yeah, for this kind of graph, the x-axis should really be down there. But one thing you could do is, if you relabel it as y = 4, that's no longer the x-axis, and that's actually not inappropriate. We've mentioned before that even the vertical axis, if it's convenient, it doesn't have to be at the origin. It could just be somewhere to the side, marking off values. So if you have, say, not this height right there, you can still write y = 4 to make it correct. But then you do have to have the 1 and 7 on your vertical axis to make it totally correct thereafter. So it might be better to just have this right here to make it work out.
Yes, thank you.
Does that make sense there?
Yep.
Awesome. Thanks for mentioning that. And this is definitely a good warm-up question for the class because we're about to do another plotting function right away. So any other questions at the moment? Okay, let's get into that next plotting one. And this is the final one that we're going to plot. So congratulations, folks. It is a lot of work to plot all 6 trigonometric functions. It's not easy sketch work, but if you follow the guides that we put down, it's definitely doable without taking too much time. So we're going to try now cotangent next. And cotangent is not too bad. Here's the reason. If you write y equals cotangent x, then what you have in the numerator is cosine. And in the denominator is a sine function, which doesn't cause us any problems. We had major problems with our plotting techniques the moment cosine was in the denominator, because we're trying to line up our vertical asymptotes. We ran into this issue right here. Secant has cosine in the denominator, so the cycle starts in a very non-standard way. And same with tangent, that's sine divided by cosine. So it also starts in a non-standard way. But cotangent is just fine. It has sine in the denominator, so it's much like cosecant. We're going to start the cycle at phase shift, and there's no weird trickery about this one. But we still have to plot it. So let's plot by doing this. We first look to where the vertical asymptotes are going to be, and they come from the sine function. So we're solving a trigonometric equation, sine x equals 0. But we can do some graphs here to aid us in that. Here's our unit circle from chapter 5. And at radian measure 0, sine takes a value of 0. Same for pi, negative pi, 2 pi, or negative 2 pi. So we can say the solutions here are x equals 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. And there are infinitely many such x's, so we put dot, dot, dot to convey that pattern just keeps on going. Another way to say this is sine x equals 0 implies x equals. What I'm doing here is taking a more familiar way to write all the zeros for sine and making it compact. That makes it more confusing, but we start to see this more and more in chapter 7. So this is more of a preview. This whole list of zeros could be reconveyed as k times pi, where k is any integer. By integer, we mean the counting numbers 1, 2, 3, 4, 5, including 0 and all of their opposites. So if k takes a value of 0, you're getting to this one. If k is, say, 3, you have the positive 3, and it generates the whole entire list. Just insert any integer. So that's where all of our vertical asymptotes will be located. What, any questions, folks, with the equation side solving? Exactly. So we'll get undefined at every single one of these values, however we specify them. But that's good in a way because it tells us at these locations, those are the vertical asymptotes on the plot that we're going to be putting in everywhere that undefined occurred. So our sketch is now starting to take form. We have our first problem point right at the origin. So I'll go like this and just convey there's a vertical asymptote by putting a dashed line through like this. You don't have to do that, but sometimes it's a good reminder there's an asymptote there. Now next we need to put down, well, let's go the positive direction, which is traditional. Next problem is right at pi. New vertical asymptote, just because sine at pi is 0. And the final one is going to be at 2 pi. I call that the final one because we're plotting both tangent and cotangent over 2 cycles. And so that means we're going up to 2 pi for these functions. So here's the last vertical asymptote. And when you start plotting these things, you might notice that sine and cosine are actually the weird ones. It's just sine and cosine that don't have vertical asymptotes. Everything else does on this entire list. Cosecant, secant, tangent, and cotangent all have this common feature. Starts at a vertical asymptote. There'll be a vertical asymptote midway when you're doing 2 cycles, and it'll always end on a vertical asymptote. Well, beyond that, though, we need a value here. This will be our pi over 2. A value here is 3 pi over 2. And we know if you take cotangent, maybe we'll plot this one in blue. Cotangent at pi over 2, that's just going to come out as a 0, since cotangent pi over 2 It's going to be cosine of pi over 2, which is 0, divided by sine of pi over 2, which is a 1, giving us a 0 right here. For the same reason, there's a 0 at 3 pi over 2. So now we got 2 points on our graph. There's infinitely many more, but at least that's a start. Next thing we need to decide is cotangent increasing or is it a decreasing function? Honestly, that's kind of tricky, but here's a trick to it. Let's look at this portion of the graph. It goes from here with the open circle, here with the open circle. Oh, and I didn't mean to delete it. Let me Control Z that. And it takes this segment of the unit circle. So this purple portion is from here to here. I circled it just so it's easily deleted. And this location, cotangent of an angle theta, is positive because both sine and cosine are positive. But over here, cotangent theta is negative because cosine flips to a negative value when you're in quadrant 2. But in quadrant 1, it stays positive. That means quadrant 1 is between 0 and pi over 2. We're up above the x-axis to make cotangent positive. But go beyond pi over 2, which is here. Helps to put it on the diagram, actually. Cotangent flips to negative. And this all shows, once and for all, cotangent is a decreasing function. It goes like this. Tangent did something else. Tangent was an increasing function, so that's kind of surprising in a way. But aside from that, they have the same kind of shape. They also start at a different location. Right at this location, whatever your phase shift might be on the other problems, is always the cycle start. Well, that means, folks, we did it. That's the last one to plot, cotangent itself. Next, we want to just write down some facts that we'll need in the next problem, example 8. But any questions at all getting that plot to go?
So like for the tangent, it's like pi by 4 other asymptotes, but this one is like pi other asymptotes.
Exactly. It's always going to be 0, pi, and 2 pi if it's the ordinary cotangent. But yeah, just like you said with this one, the deal with tangent is cosine goes to 0 at pi over 2, 3 pi over 2, and so on. And so that's why you saw the asymptotes in these locations.
Oh, okay. Yep. Thank you.
Other questions at the moment? That's exactly what it is. Yes, if you multiply tangent by -1 and then put something inside x plus pi over 2, that's exactly what you're dealing with. And actually, we saw lots of stuff kind of along those lines. For a related example, if you're looking at, say, a sine function. Let's plot this over a more reasonable domain. Let's say 0 less than or equal to x less than or equal to 2 pi. Then here's your sine function. But now plot y equals cosine x. This one is on a domain 0 less, that helps if I move that out of there, less than or equal to x, less than or equal to 2 pi. And notice that if you flip cosine around and move it, well, you would potentially have this basic shape, except you'd want to go negative pi over 2, 3 pi over 2, and now it looks really obvious that that function in blue is the co-function to the one in red. If you look at just the right location here, phase shift the one in blue, and you're back to sine. Tangent and cotangent are similar, but you also have to flip them around like you mentioned. And that's one of the reasons we call them co-functions. It's not a big change from their original parent functions when we go to plot them. Well, other questions or comments so far, folks? Okay, well, let's write down just a couple other facts about this. For our cotangent function, this is one complete period. So the period is equal to pi itself. That's this distance going from here up to pi for a period of pi. We plot this over 2 cycles to make it interesting, but also it's a familiar pattern with all the rest of the trigonometric functions, so it feels less jarring if we do 2 cycles. There's no amplitude, and the cycle starts right here. Whatever your phase shift is, that's where we'll start. Well, other things that we should mention is if the period is pi, what is the increment? The increment on this one is half pi. That gets you to the x-intercept, so that's the location we want to take. So 1/2 pi for increment, and that's the same exact deal for cotangent as well. So tangent and cotangent have this weird feature. The period is half as much, and increment is 1/2 pi, not 1/4 pi. With all the information, we're now about ready to do a transformation of cotangent. And here's the function we're looking at. It looks awful. We promised we're doing this one mainly because sometimes there's fractions in the homework, and I feel like we should do one that involves fractions most definitely and see how it ought to go. This one's the same exact instructions for tangent plotting. We're going to state period and phase shift to start, plot the function over two complete cycles. Sorry, that was a tongue-tied word there. And all the other stuff. We want the vertical asymptotes, all the x-intercepts. We'll label the y-axis to indicate its scale. You know, that's one thing I forgot on our plot above. Let's add a little bit more for y-axis. That one's a trick, but it's the same trick that we used for tangent. If you go to this value, let's put this in purple to make it pop out. This value is at pi over 4. And we could verify cotangent pi over 4. That'd be cosine in the numerator, root 2 over 2. Sine in the denominator, root 2 over 2. That means it's just a 1. So at pi over 4, that's where we can set the scale, because this height would be a 1. But if there was, say, a 3 right here, that would be a 3 instead, like we did for the tangent function. So sorry for jumping the gun on this one. This is definitely good to put down here, because this indicates the y-axis scale. Well, any questions, folks, with that last addition to the notes here? Okay, I think we're ready to get started. So here is our final plotting problem on these notes, at least. It's f of x equals -1/2 cotangent an 11th x plus pi over 22. But no matter how ugly it gets, the process is the same. We're going to grab the period. We need to be careful because tangent and cotangent have period pi, not 2 pi. This is one of the odd ones out on this list right here. Let me see if I could display it a little bit better. On this list right here, watch out for the period. It's in red because that's some big change from all the other functions. Then beyond that, just like the problem we started off with today, we just divide by this or multiply by the reciprocal right away. So this will become pi times the reciprocal, 11 over 1, for a good old 11 pi on this thing. So interesting period. Next thing we need is phase shift. Where we look for phase shift in the problem is right here, including the sign, because we now need to negate whatever it is. So from here, we'll pull -pi over 22. You'd multiply this by 11 over 1, but that could look weird in the notes. I'll write it out this way just for a paper trail if you come back to this problem. Divide by 1 over 11. And now more fraction arithmetic. This becomes -pi over 22 times 11 over 1. We get a nice cancellation going this way, leaving us with -pi over 2. So we're through with this portion of the problem. We have the period and phase shift. Now we're going to do the other analysis for increment, the start, and the end. Any questions to this stage so far? Okay, so let's put down increment first. Not that it matters a whole lot on this problem, but that might not be a bad way to start for these. Increment is, just another warning on this one, non-standard. This one is 1/2 pi, so that's why it's red here on the notes. And so this will turn into 1/2 times, I said 1/2 pi, sorry, that's 1/2 times period, and the period is 11 pi. So 11 pi goes here, and we get altogether 11 pi over 2. Well, we're just about there, folks. Now that we have the increment, we're ready to say the start and the end on this one. So the start for hit this, because it's not tangent or secant, it's just the phase shift. That's the typical one, and phase shift on this problem was -pi/2. Next, the end of this, here's where I need a reminder for myself. That's why I put this in yellow. We're doing 2 cycles, so the end should be phase shift plus twice the period to get 2 full cycles of the cotangent function. I'll put that in yellow just to connect this thought from the instructions to why the formula looks like this over here. So phase shift was the -pi/2. I'm sensing I need a little bit more space here. That actually should work out. Let me look at my work here. But I think I do need a little bit extra work for the arithmetic. So for phase shift, I'll put in -pi/2 to start, plus 2 times this, so twice 11 pi. Now it becomes -pi/2 plus 22 pi. But then we definitely want to simplify this as much as possible to make life easier. So we'll multiply this by 2/2 to get -pi/2 plus 44 pi/2. We're almost there, folks. So it tells us the end on this one is 43 pi/2. Think of this equality for n tracing all the way to here, and that's finally where we're going to end up, 43 pi/2. Okay, I forgot how kind of nasty this one actually is. A little bit worse than the homework problems, I think, but it's good to deal with things that are just not designed to work out nicely like this one. I wouldn't do that on a real exam, though. For the real exams, it'll be a little bit cleaner so we can focus on the concepts and less on that. Well, any questions, folks, before we go to the next step? Okay, well, I guess the first step is one long horizontal axis. That's definitely what I do first. Then let's look at where we're starting. -pi/2. Then our increment is 11 pi/2. We're just going to continually add plus 11 pi/2 to get all of our other values. So the next one is going to be add 11 pi/2 to this to get 10 pi/2. Add 11 pi/2 again. Now we're at 21 pi/2. Next one is going to be at 11 pi/2 for 32 pi/2. Then add 11 pi/2 to that, and that's going to be 43 pi/2. At this point, we have 5 tick marks, so we should double check 43 pi/2 with that value there. If everything looks good, then that means, hey, we're all set up, and we're ready to begin with the vertical axis next. So for vertical axis, you can place it anywhere, but I'll place it close to -pi/2. Where the red dot is about there, I'd say is about the origin. Maybe not perfectly placed, but that is okay. So we have an axis going that way, and I feel like I should try a little bit harder with that axis. Let me scroll just a touch. There we go. So we can see this a little bit better. Here's my vertical axis. We are going to use this 1/2 eventually. But I would say ignore it for the moment, as weird as that sounds, because we need to put down the plot for the actual cotangent before we know where this is going to go in to set the scale. So first thing we do is, for plotting cotangent, it will start on the vertical asymptote. That's by design. So there's our first vertical asymptote. Then the next position is always at x-intercept. That's because we're using this increment to direct us to it. So here's a solid dot. Then it just keeps on alternating. Vertical asymptote, another x-intercept, then another vertical asymptote. And from here, we're about ready to start plotting. Now, when you go to plot cotangent, the mental image we need in our mind is this one. Cotangent is a decreasing function, but we should look before we leap. Is this really decreasing or is it increasing? Or in other words, there's something nasty in that transformation up here that's going to really affect how we plot this. Anyone see what the problem is in this function that causes just one extra issue?
Is it because the -1/2 is actually positive?
Well, the negative right there has to stay as a negative, but what it'll do is it'll take this whole graph in blue and now flip it across the x-axis. So we went from a decreasing cotangent function, put a negative there, and it's actually increasing on us out of nowhere. So our plot should look a little bit more like this. Starting about the asymptote, it increases around, well, that's kind of a weird plot. Let me try a little bit harder on that one. It starts to increase along this way. Then on the second one, we're just trying to duplicate it as best we can. We'll let that one stand. But to me, that's already really pretty tricky. Let's see if we can add a note to this. That negative sign right there means flip across x-axis. So that's why we have this curve. It looks more like a tangent rather than a cotangent. Now, last thing to do, we need to set the scale going this way horizontally. We have a 1/2 here, and so we go like this. Take a value midway from here to here, or it could be a value right here, midway between an asymptote and the intercept. If you go this route, you take a point right here and go horizontally to the left. This will be at height +1/2, and that's already set the scale at that stage. But you could throw in -1/2 right here as well. So at that stage, we've pretty much done it, folks. This is the complete sketch for cotangent. This is about as bad as it could ever get. Transformation of cotangent. Well, any questions at all, folks, on getting through that one? Okay, well, this deserves congratulations, folks. Usually there's a sigh of relief after getting through all these plotting problems. And as a reminder, I mentioned in class last time, I'm thinking of assigning or putting 3 problems from this on an exam. It'll be 2 or 3. I'd have to control the length of the exam. If it's 2, I'm pretty much going to use a random number generator to pick 2 of these. If I go for 3, I'm going to go row by row and use a coin flip essentially to pick one or the other for these functions. You won't have to plot all 6, but you have to be ready to plot all 6. And for the purposes of the exams, knowing these original plots is going to be very essential to getting the sketches to go through. So that's something we do have to memorize. And because of that, on the assignment number 6, I put a problem right over here where we're just going to do some simple sketches of all 6 trigonometric functions, no transformations. Think of this as massive practice to help you support plotting techniques when you go to do the actual exam too. Well, I think that's all I have to say for these notes. Any last questions, folks, before we save them and go to the next section? Okay, it looks like
I do have one question.
Yeah, go ahead.
So obviously with cotangent, if the number is negative, we flip it across the x-axis. Or what would be would it be the opposite with tangent then? If it was negative, we treat it as a cotangent. Would that mean it would be decreasing?
That's exactly right. Absolutely. Let's take a look at our tangent on this one. So that would be this one right here. Because it was a +5, it's increasing like normal. But if that was a -5 like this, our sketch would have went this way instead. Does that make sense with that issue there?
Yeah, no, just looking for clarification on that, but thank you.
Yeah, you bet. Well, let's now go to the next section. The next section is weird at first, but I assure you it starts to become extremely familiar before very long. We're now going to start to invert our trigonometric functions. Not as bad as it sounds. We have 6 trigonometric functions. We can define an inverse for all 6 of them, but we're only going to invert 3 of them: sine, cosine, and tangent. Those are the most useful ones in engineering, calculus, and those kinds of courses. Yes, it would be that sine -1, arcsine. So that's what we're going to get into: arcsine, arccosine, or sine inverse, cosine inverse, and same for tangent. This right here is just some review material from college algebra. This is optional reading. But the major meat that we need is carried right inside here, section 6.3. This is the major stuff we need to get started on inverting at least one of these functions. And let me show you the trouble of trying to invert one of them. First, well, there's a lot of thoughts to connect here, really three different concepts: one-to-one, horizontal line test, and invertibility all go together. This one's a pretty technical definition, and college algebra doesn't study this a whole lot, actually. Math classes start to pick up on it a little bit later, like linear algebra. One-to-one means if your function values ever match, the inputs A and B had to have been identical. So we're interested in one-to-one functions. Those are the only ones we can invert. But to tell if our function is one-to-one, we use the horizontal line test. Function is one-to-one if and only if every horizontal line intersects the graph at most once. Sine is not one-to-one. That's why this seems like a really weird section, right? Everything here seems like a lie, because just as you said, sine goes like this. And you can draw a horizontal line that intercepts it infinitely many times because it's periodic. It will just keep on hitting that line over and over and over again. So it feels like class is over. We can't invert these, right? Except there is always a trick. Mathematicians, never content to leave well enough alone, have found a way to invert these kinds of functions, even though they don't seem like they could be on face value. But we're going to connect this thought. We want our function to be one-to-one to make it invertible. One-to-one is conflated with horizontal line test. So if our function passes a horizontal line test, it will be invertible. Let's take this to Desmos and see what we're dealing with. We're trying to invert sine x. Let's kill that one. And like we said, that is absolutely not invertible, right? It fails a horizontal line test the moment you go right past this dot. So if we ended it right here, pi over 2, that's an invertible function. It's just not your original sine function. It's been restricted to a smaller domain. And that domain is way too small because we want a function that takes a range going from a height of +1 down to -1. We want the same range as the original sine function. So what we do is we go backwards. That's an invertible function, and it carries the entire range from -1 to +1. We can invert on this thing. We worked really hard on plotting these functions, so for this example, notice it's not numbered. This is just notes, really. We'll make Desmos do the heavy lifting for us. So here's the plot of sine. Let me make that a little bit smaller. But it's not your original sine function. It has a name that's not often given. This is the restricted sine function. Because there's an exclamation mark, because again, this is kind of weird mathematics at first, if you haven't seen this kind of work being done. College algebra tries to do this kind of stuff, but there's not a lot of time to really get into these topics until we have to. Trigonometry is where we really discuss this kind of work. So the restricted sine function, observe, it will pass a horizontal line test. Every horizontal line intersects at most once. That means you can invert the restricted sine function. Let's put down some extra information on it, though. It went from -π/2 to +π/2. So this restricted function has domain with a bracket to include -π/2 up to +π/2. And we chose that range specifically from all the way to -π/2 to +π/2 because it contained the whole range of sine itself from -1 to +1. So the range of the restricted sine function did not change. The only thing that did change is the domain. Well, we've got our domain and range set down. Let's put down a couple other points on this. This point is at location -1 π/2. This point is at location π/2. positive 1. And there's a really great trick here. If you want to plot the inverse, that's the thing we're going to do next, all you do is you swap those 2 points. So it's going to be first point at pi over 2 negative 1. Second point will be at positive 1 pi over 2. Let's do that one by hand, just because it feels a little bit more nice in a way to do our actual honest by hand sketch. Here is our sine inverse function. Let's give this a title. Y equals sine inverse x. When we say and its inverse, we're referring to this as a function. Just like in mathematics, this is not an exponent. It's just saying inverse function. Like if we said f inverse of x, for an example. So next thing we can do is we take this point. We're going to, oh, hang on. Let me take a look at that. Sorry, that should have been an easy step, pulling the coordinates. That should have been negative 1, negative pi over 2. There we go. So flip those coordinates. We have negative pi over 2 coming out, or hang on. Sorry, I did make a huge mistake on that one. Must be late in the week. So coordinates should go x coordinate first, right? So negative pi over 2 to start. Good things happen in 3, so 3 tries is about right to get this one in. And the y coordinate is negative 1. Phew, sorry folks, that one was really hard for me, but I think we got it this time, the third try. Now we've changed those coordinates. We'll go from negative 1 to negative pi over 2 down here. Here's our first point. This point is easy, it's 0, 0. So switching that one, no big deal. There's 0, 0. Switch this one and it'll be positive 1 pi over 2. Gives us a new point right here. And it's actually kind of hard to sketch the graph because it's not a straight line. What it's really doing is it's reflecting this line right here across y equals x. Invertibility causes a reflection across that line. That helps us to sketch because then it tells us it should look about like this. So there's our restricted sine function. And to test if we got it at least close, let's also plot it right here. Y equals. In Desmos, I think it's a little bit, oh, sorry, I wasn't trying to cover everything up. I wouldn't type it this way in Desmos, sine inverse. I think it's easier to just say arc sine, which is the same exact meaning as sine inverse. And here's our arc sine x. It reflected across the line y equals x. So that's the inverted function. And in red, that's the restricted function. Now, the thing that's nasty about this is people call this restricted function sine x, even though that is not sine x. A function comes in 2 components. The definition for calculating, that's the sine portion, but also the domain. If you've changed the domain, you've changed the function, but for one reason or another, we still call it sine x. We just have to know from context that it's not your ordinary sine function. Well, any questions, folks, with the diagram so far? Okay, so the good news is you can, in fact, invert every single one of these trigonometric functions. The bad news is it's not a full inverse. We are changing the function to make it happen. And if we do that to all the other functions that we're plotting, sine, cosine, and tangent, and their inverses, here's the short of every one of those. So we just did sine, and below is the sine inverse plot. Cosine is different. It starts at its maximum. So the range of cosine goes from 0 to 2 pi right over here. Let's put this on the plot just so it's easier to see. This is at pi over 2. This one's at negative pi over 2. And tangent is also kind of unusual. This tangent plot has a vertical asymptote right at negative pi over 2. Another vertical asymptote right at positive pi over 2. But that means when you go to the inverse function, everything switches. A vertical asymptote like this one becomes a horizontal asymptote at height y equals pi over 2. This one at negative pi over 2 becomes a horizontal asymptote at y equals negative pi over 2. And here's our information about the restricted domains. Cosine is going from 0 to pi on this one. But look at tangent. This one's a little bit trickier. Notice that there's parentheses around the restricted tangent function, and that means you can't actually hit the negative pi over 2. That's the vertical asymptote. So that affects the range right over here. Whenever we calculate on tangent inverse, the only potential values you'll ever get, unless you're going to complex numbers, for example, are from negative pi over 2 to positive pi over 2 in those parentheses. But the domain on that one is all real numbers. And here's the domains and ranges for the other restricted functions. We're actually going to look at these extremely closely, because when it comes to calculating with a restricted function and its inverse, it is all about domain and range extremely heavily. So we'll emphasize that on every single problem by returning to this table. This will be a table that I'll print on the exam as well as extra support. So there'll be two elements on exam 2, this table and the summary of plotting techniques that we've been working on. So this is our one-stop shop for looking up information about the restricted functions. And down below is just some notational things that we've been hinting at. Sine inverse is a traditional way to write it, but there are very good reasons for writing it out this way, arcsine. Sometimes it might be it's just easier to type into Desmos, but other times you're trying to avoid a miscommunication. Same with cosine. It might be referred to cosine inverse or arc cosine. We might say tangent inverse or arctangent. But here's a reason why sometimes people like arcsine, arc cosine, arctangent. Sine inverse here is a true inverse function. This one is a reciprocal function, and notice how awful that is. One small change in your notation makes all of the difference. You put your power here, and you take a reciprocal to get cosecant, but sine inverse is absolutely not a cosecant function. Even though with power 2, that is a right pattern. Power 2 right here does mean you're squaring the function, but not so with a -1 right here. That's kind of dangerous notation in a way, so we'll be careful with it when we use it. So that's the notation. Here are the information that we're going to work with. And we have about 2 minutes and some change. Let's do a couple computations, nothing major. We'll make sure we end class before the last minute. So here's a huge list of things we're going to calculate. Let me show you the thoughts I would have every single time I do an inverse function. I would take a look at what we're inverting. All of these are sine, so we can focus on just those. But sine inverse has domain, -1 to 1, and range, negative pi over 2 to pi over 2. We definitely want to convey that on a unit circle, because that's where we calculate these things. So let's go from negative pi over 2 up to positive pi over 2. And right here, let's see if I can highlight that a little bit better. This is where all of our values are going to be for sine inverse. They must lie on this strip in bold. That means everything out here is a true restriction. I'll convey it that way by those little lines to say we are not pulling any values from here whatsoever, which is kind of weird. Now we're ready to get started, and anyone happen to know the value for this one? Arc sine or sine inverse of -√3/2.
Is it 1/2?
It wouldn't be 1/2, no. But
Would it
one thing
be
you
two?
could think of, sorry, say again?
Would it be 2 because it's inverse?
It wouldn't be 2 either. From class, Michael was saying it's going to be an angle, and that is the right thought on this one. This was the input, which was the output to the original sine function. Arc sine now gives you an angle. But here's a cool way to think about this. -√3/2 is about here. It's about a -0.9. Now, reverse engineer the angle by going to this spot. You just have to say, what is that angle right there? It is not 5 pi over 3, unfortunately. Why is that? Because sine inverse takes a range from here. Anyone happen to know what that angle might be? It turns out it's a negative angle. Oh, and let me go this way. Got it.
Wait,
So
wait, wait.
negative. Sorry, go ahead.
Oh, never mind.
Is
Oh,
it negative 60?
yeah.
It wouldn't be negative 60, but this angle right here would be negative pi over 6. And that value right there came from the negative root 3 over 2. Negative root 3 over 2. And so this is negative pi over 6 itself. Here's the check on this one. If you take sine negative pi over 6, you do in fact get negative root 3 over 2. And this is what inverse functions always do. The inputs and the outputs always swap in that way. So if you think of how did you calculate sine negative pi over 6 through this diagram right here, you're just doing the diagram backwards. You start with the value on the y-axis, grab the angle, and that's your answer. We'll practice that a whole bunch when we come back from the weekend. But any questions, folks, for this problem here? Okay, sorry, I was trying not to run to the last minute, but it happened anyways. Have a great weekend, folks, and when we come back, we'll be doing more practice like this. Honestly, all it boils down to is chapter 5 work. If you memorize where all your angles are on the unit circle, then that's going to be really great support on getting through inverse functions here. But have a great weekend, folks. I'll see you all next Tuesday.
Thank you.
You bet. Thanks. Thanks. And thank you. Thank you. It always seems kind of awful how inverse functions, they just keep coming back. It's abstract stuff, I always felt like.